In this video, we will be covering how we created our camera controller. Camera controllers have been around for as long as 3D games have been a thing. The general idea surrounding camera controllers is usually consistent between games, however there are many variations. In Mario 64, the camera controller defined what camera controllers should be today, smoothly pivoting to track the player as they run around and following them when they move out of range. The controller also allows the player to both zoom, rotate, and pan around in first-person view. As a second example, Wind Waker included both a lock-on mode and a strafe mode. Combining these two and the GameCube's C-Stick, Wind Waker gave the player slightly more freedom. Monster Hunter World, as a more recent example, slightly deviated from how Mario 64 and Wind Waker handled the pivoting of their camera. When the player inputs a horizontal command, both Mario and Link run around in a circle as the camera remains anchored in place. However, in Monster Hunter World, the player would move straight with the camera following. Another noticeable change is that certain walls will apply a dithering effect when the camera is obstructed, while the others didn't, as far as I can tell. Despite these changes, the camera controller has remained largely the same. Today, we will create our own simple camera controller and attempt to emulate what we've seen in Unity. Here we have a scene with two cube game objects, one to act as our ground and the second will be our substitute character model. The texture on the ground is by Gridbox prototype materials, which can be found in the asset store. Once you have that set up, we'll create a new C# script and name it comp player inputs to handle the inputs. Add it to our player and open it up. Let's start by deleting both the start and update functions and surrounding our class with a namespace. I'm going to use HamJoyGames. Then we'll add a few constant strings, mouse X string, mouse Y string, and mouse scroll string. These three refer to Unity's input manager, and you can find them by going to Edit, Project Settings, and going into the Input Manager tab. Here you can see the fields for mouse X, Y, and scroll. These fields or axes can be called by their string. Going back to our script, I'll create three public properties to access the mouse input. Our first public property will be called mouse X input that will get the value of the access of mouse X string. And we'll do the same for the other two. We'll create a second script and call it comp camera controller and add that component to our player as well. Open up the script, add it to our namespace, and remove the start and update functions. We can add them back later. So how the camera controller will work is we'll take input from the mouse and use that to rotate the camera, and then based on the camera's rotation we'll reposition the camera in order to focus on whatever we're following. To start, we'll create two variables, one for the camera and one for the thing that we're following. We also made them both private because we don't want them to be accessible outside of the script. However, we do want them to be visible within the inspector, so we'll add the attribute called serialized field to both of them. We will then add a header called framing just to group them within the inspector. Now, going back to the editor and looking at the inspector, we can see two fields that we can assign. Click and drag the camera and the cube to their corresponding variables. Going back to our script, we'll define some more private variables. One will be a vector3 called planar direction. This variable will represent the camera's forward on the XZ plane. And then we'll create a quaternion called target rotation. Next, we'll bring back our start function. Here, we'll set the planar direction to be equal to the follow transform.forward. This is important because we need to assign the start position for our planar direction. We will also set the lock state of the cursor to be locked. This will hide the cursor as well as locking it within the game. We'll now bring back the update function and check if the cursor is locked every frame. If it isn't locked, we'll return. This gives an early out and prevent the rest of the update function. As a result, this will stop the camera from moving if the cursor isn't locked. So what we want to do is handle our inputs. We'll create a local variable called mouse X, which is equal to the static property that we made earlier. Since it's static, we don't need to call it as an instance of a class. We can just use the class name itself. In this case, we'll use comp_player_inputs.mouseX_input. What we want is to take the input from the mouse X and apply it to the rotation of the camera on the Y axis. So we'll rotate the current planar direction by the rotation generated by our mouse X. We'll use the draw line debug just to visualize this in our project. In the editor, we can hit play, focus on the camera, and see what the planar direction is and how our input affects it. You can see the red line moving around the cube as we move our mouse left and right, meaning it's working as intended. Then we can take the planar direction and convert it into a quaternion and set the rotation of the camera to this new quaternion. Quickly, we'll just test it again in the editor and see everything is working. To handle the rotation on the x-axis, we'll start by creating another header called rotation. We'll then add more private variables required for our vertical rotations. One will be a private float called min vertical angle, and we'll set it to -90. The other will be another private float called max vertical angle, and we'll set this to 90. To make these values more intuitive, we'll limit how high and low each of these values can reach when modifying them within the inspector. To do this, we will apply another attribute to each of them called range. For the minimum vertical angle, we'll set the minimum to -90 and the maximum to 90, and we'll do the same to the maximum vertical angle. Lastly, we'll add another private float variable called target vertical angle. In our update function, we'll now handle the mouse Y input. Start by adding in a private float named mouse Y and access the mouse Y static variable like before. To calculate the target vertical angle, we'll sum itself with the mouse Y clamped to the min and max. Based on the target vertical angle, we can get the rotation of the camera on the x-axis using quaternion.euler and apply it to our target rotation by multiplying them together. Testing this, we can see that we can now look both vertically and horizontally. With the handling of the rotation done, we still need to handle the repositioning of the camera, and for this, we'll need a few more variables. First, I'll create another header called distance. Then we'll create a private float variable called min distance, how close the camera can be to the player, another private float variable called max distance, how far away the camera can be from the player, a private float called default distance, how far the camera should start away from the player, a private vector 3 called target position, where the camera should be, and a private float called target distance, how far the camera should be from the player. In our start function, I'll assign the target distance to our default distance. Then in the update function, we'll need another input value. Here we'll create a float called zoom, which is assigned mouse scroll input. I'll invert the value to make it so that scrolling down zooms out and vice versa. So now, to calculate our target distance, it will be similar to how we did our target vertical angle. Instead, we'll pass in the target distance plus the zoom input and clamp that to our min and max. We then use this distance to get our target position. We do this by taking the follow transform and moving backwards based on where the camera is facing, by the magnitude of the target distance. So it will be the focus position, subtract the target rotation, multiplied by vector 3.forward, multiplied by the target distance. We can now take that target position and apply it to our camera. With the basis done, it's time for a bit of cleanup. Instead of creating a vector 2 as shown in the video, create a private vector 3 called framing with an initial value of 0, 0, 0. This will be used as an offset from our follow transform. Next, I'll add some Boolean variables that will tell us whether our axes should be inverted or not. This will let players match their preferences. I'll name them as invert x and invert y. We'll then create a default value for our angle similar to how we used a default value for our distance. I'll give this a value of 20. Then we'll use a special function called onValidate. OnValidate is called every time a value in the inspector is changed. All we're going to do here is ensure that our default values are within our min and max values. So default distance will be itself clamped between the min and max distance, and same goes for our default vertical angle. Inside the start function, I'll do calculations similar to what we did in the update function. We have our distance already, so for our target vertical angle, we'll set it to the default vertical angle. Then we'll copy and paste the target rotation and target position lines found in the update function and put it in our start function. Inside the update function, we'll use two if statements to check our inverts and apply them accordingly. Next, we'll create a new vector3 called focus position and assign it the value of the follow transform dot position and add the offset of the camera by passing framing into the camera's transform direction function. This will replace the follow transform dot position value located in the target position assignment line. Now we can test our camera in the editor to see if the inversions are working, the min and max angle properly limiting how much you can angle the camera, the min and max distance properly limiting how far and close you can be from the point of interest, and the framing successfully offsets the camera. Currently, the camera can move through objects. To fix this, we'll have to handle the obstructions. Back inside the camera controller script, we'll add another section called obstructions. I'll create a field that will define how big of a radius that we want our spherecast to check, called check radius. We also want to be able to filter out what layers we want to check against. I'll create a layer mask called obstruction layers and assign it a value of -1, or all layers. Lastly, we'll create a list of all the colliders that we will ignore, and I'll call this ignore colliders. In the start function, we will add all the players' colliders to the ignore list. To do this, we will check the children that this script is connected to and get all the components of type collider. In the update function, we'll handle the obstructions. We'll start by adding a new local float called smallest distance and assign it the target distance. I'll use a spherecast to check all the colliders between the player and the camera and store them into an array. To do this, we'll first create an array of hits and utilize the physics.spherecastAll function. In this function, we need the origin as focus position, the radius as check radius, the direction as target rotation multiplied by the negative forward direction, the max distance as target distance, and the layer mask as obstruction layers. We'll check if there are any hits at all, and then we'll go through each hit and check if the obstruction appears in the ignore colliders list. If the collider is not ignored, we'll check if the hit distance is less than the smallest distance, and if it's smaller, in other words, the collider is closer than the camera's current distance, we will update the smallest distance to be the hit point for that collider. Then we'll replace the target distance variables under the target position line and replace it with the smallest distance variable. Back in the editor, you can see that our obstruction layer currently accepts everything. If I were to create two walls, one having a new layer called camera ignore, while the other staying as default, change obstruction layers under the camera controller to be everything except camera ignore, and then run the game, the wall with the new layer would not affect the camera, while the other would. With that, obstruction detection is now complete. Now we need to work on smoothing our camera positions and rotations. Large changes or lag can make instantly moving the camera to our targets jittery. To fix this, we'll use both linear and spherical interpolation. First, I'll create a serialized field called zoom speed with a value of 10 under distance, and another serialized field called rotation sharpness with a value of 25 under rotation, as well as two more private intermediates called new position and new rotation. Firstly, to control the rate at which we zoom, we'll multiply the mouse scroll input by our zoom speed. Then, to smoothen out the rotation, we'll use slurp to generate a rotation based on our current rotation, our target rotation, time, and our rotation sharpness. We multiply sharpness with time in order to make rotating time dependent instead of frame dependent. Next, we'll do the same for our position. We will lerp from our current position to our target position and move it based on our time multiplied by rotation sharpness. You could replace this rotation sharpness with a position sharpness variable. Well, this works fine. Lastly, we will apply these new values to the camera by assigning camera.transform.rotation with new rotation and camera.transform.position with new position. Back in our editor, we can now test the smoothness, change the zoom speed, and the rotation sharpness to values that are suitable for your needs. In our case, we changed the zoom speed to 5 and the rotation sharpness to 50. So, that's the end of it. It doesn't have everything, but it's a good start. I hope you enjoyed this video. Feel free to leave comments below about how you felt about the content and delivery of the video. Your feedback is very much appreciated. Next up, we will be covering our character controller. We hope the combination of the two will be sufficient enough for you guys to use. Thanks for listening, and I'll see you in the next video.